Hello, good evening, everyone. We will start with the session today. I hope I am audible. Let's just get started. The content for this covered is like different type of devices, which are like mainly these passive microwave devices, which are like all the one port, two port, and three port, four port devices. So for one port, for example of one ports devices are your matched load or short load or open load. Similarly, the example of two port devices are and bend and then like there are uh, trans transmissions, actually transitions, which are used to couple two different kind of waveguides. So these are transitions and like attenuators. And the example of three ports, also this isolators. And examples of three port device are circulators and Ts. And the four port devices are hybrid, are couplers. So which are hybrid. Uh, so there are different type of couplers are there. One example is hybrid coupler. So these are few important devices with the with the microwave. So basically, so bend basically you do like to avoid like the you can have if you have very sharp bend like this in the microwave transmission line. So basically this causes a loss actually. So to prevent that loss, either a continuous gradial this bending is there, which prevent the electromagnetic radiation from happening, and like some lesser compared to sorry, just my network got lost. There are this bend, and also you can construct this bend like this. So just you do it uh, uh, you do it like this, like just tapering at the outer edge, or you can do circular also. So the rule is the radius of the circle should be equals to 1.2 times 1.8 times of width. So in case of this flat band, this width should be a if this should be equals to 1.8 times w. So this is the ground rule for bends. So then there are discontinuities. So suppose you are matching a different transmission line. So also that can be modeled as a mm, as a as a two port devices. So suppose you are matching a like coaxial line to SMA line, or a coaxial cable to SMA cable, that constitute as a discontinuity. So that can be modeled as suppose that can be modeled as so basically like this you can write like this. So the central conductor is different for two lines, and that basically you can model as series or shunt RLC component. Also, you can map. So this can be mapped as this shunt capacitance. Also, you can construct a gap implementation basically. So what you do, you just take this transmission line, and you just put a gap, and this distance control this capacitance between these two lines, and basically this can be constructed as a gap capacitance, and this can be modeled as a capacitive coupling. Also, you can model inductive coupling basically. That if you in the transmission line, basically, if you suppose you have a waveguide, and if you create a within that waveguide, if you create a so within that waveguide, if you create a aperture like this, so if you put a aperture like this here, and similarly a aperture like this here, then basically this can construct can be modeled as a inductance actually. So this equivalent circuit of this is basically is a inductance, or you can call as a inductive coupling. So this also like there are different kind of sorry, I think I lost the network. You can see that transitions also. Suppose you want to convert from SMA port SMA to BNC, then you can have some transition or some coaxial to waveguide, or a rectangular waveguide and other kinds of construction. Then you can have those transitions and those which are like this. So suppose in this waveguide you have this which connects to the transmission line. Also you have this pi by 2 length transmission line. So basically, and then basically is a coaxial line, and which so the electric field in this direction. So with this line, the fringing field will be this direction, and from this side, the reflected field will constructively interfere here, and you will couple the electromagnetic energy to this transmission line basically, to this waveguide from let's say this is coaxial or BNC coaxial or SMA type of connectors, or then BNC or SMA type of connectors. Then basically you can couple to these lines in this fashion. So these are the few examples of two-port devices, and basically there are other examples are like mode suppressor, which separates a particular kind of modes, and the other examples. The so these are basically two-port devices. The bend and those uh, attenuators and isolators are two-port devices. Also, you can have circulator devices, which cause also there are circulators and power dividers also. So which divide the power into each two branch. So those kind of devices. Uh, there are different kind of combinations are there. So there are different type of devices are there as we discussed in the class. So they can be T, circulators, and power divider. So there are different kind of categories are there in this. So one is lossless, reciprocal, and uh, and uh, and matching. So in the T, like you have lossless and reciprocal. In the circulator, it does not match, and with the circulator you have uh, lossless and matched but not reciprocal. And then the power divider, you have basically uh, it's not lossless, but it's matched and reciprocal. So these kind of different kind of devices are there. So in the T there are two kinds of T's are there. So one is E plane T and other is H plane T. So in that basically like the direction of the electric and magnetic field decide which kind of plane T is there. And also there are circulators which uh, so circulators are the device. So basically you have three ports. So let's say one, two, and three. So from one to two, the power transfer will take place, and the power from two to three power reflected power will pass, and from three to one is rejected actually. So this kind of devices basically you can use for you can use for duplexing the thing. Suppose you want to do transmission and receiving with the same antenna. Suppose you connect an antenna with the port two. So let's say you connect the antenna with port two, which is radiating also and which is receiving also. Uh, so basically, what has happened? Receiving it will receive the power, and it will just power will get into the port two, and the transmitted power will fed to the port one, and basically port one power will goes to port two and will pass to the antenna, and the power received will be input from a port two, and it will be passed to port three. So basically, that can be used for duplexing the for both receiving and transmitting kind of signals. So in that, basically, these circulator kind of devices are useful, and this is non-reciprocal because the power does not go from port two to port one, but this is not allowed. Similarly, uh, so this reverse is not allowed. So that's why it's a non-reciprocal devices. Right? So that is about the circulator. So yeah. So similarly, there are power dividers also are there. So there are different kinds of power divider are there. For example, normal power divider T based or this Wilkinson power divider, which in which like the output. You can model a power divider, normal power divider by just equivalent line transmission line in this. So if this characteristic impedance is Z naught by 3, Z naught by 3, Z naught by 3, then basically if you have input impedance Z naught at the input of 3, then all other ports will be matched, which will be have Z naught output impedance. But the problem with this kind of devices are that like this is port 1, this is port 2, and this is port 3. And if there is some power reflected from port 2, it will be transmitted to port 3. So this port 2 and port 3 are not isolated. So basically, if these ports are not isolated, so then there is different kinds of power dividers is there, which is Wilkinson power divider. So basically, like from port two to port three, in that basically destructive interference will take place, and which isolate port 2 from port 3. So these are the few examples of 3 port devices. So and the other 4 port devices are couplers. So the example of this is like the normal 4 port couplers. So suppose this is one, this is two, this is three, this is four. So one to three transmission will take place. One to four will be a coupled port. A fraction of power will be transmitted to fourth, and two will be isolated. So the one to two very less transmission will take place. Similarly, from three to two, there will be some fraction of power will get uh, will be there, and 3 to 4 will be isolated. So these kind of devices are used in those to couple power, or to measure power in transmission line in real time. So there are different kinds of couplers are there. So basically, like that depends on like the phase of the different input and output port. So basically, so the coupled port are, if the coupled port are is couples and output ports are 180-degree phase shift, 180-degree phase shift, then those are known as like the hybrid couple. If the coupled and through ports are have equal powers, then those are known as the hybrid couplers. And in the hybrid couplers also there are different kinds of categories are there. One is 180-degree couplers, or so one example is 180-degree couplers, and other one 90-degree coupler. So this is Magic T and Rat Race T, and these are coupled line and branch line. So the magic tree is basically the superposition of E plane and H plane T, and basically the the advantage with the magic T is like the other 2 ports are basically isolated from the third port. So those kinds of devices you can are basically primarily used in the microwave circuits and microwave communication. Also, there are end launchers which are used to couple from a PCB, let's say microstrip lines to the actual coaxial cable. So these basically, suppose you have a line at the PCB. So let's say you have a microstrip line at the PCB. So basically, they some kind of end SMAs are used to which couple this to this outer coaxial line or SMA cables. So these kind of devices are used primarily in the microwave engineering. So with this, I think this was the summary of this week. I think let's just get started with the problem solving session for this week. If you have any doubt related to the content covered in the class or today's session, you just ask, or otherwise we will move to next problem solving session. Okay, so I think let's just move to next problem solving session. So this uh, first problem talks about this. A 50 ohm microstrip line is shown below, designed on the substrate with dielectric constant 2.2 and a height of 1.6 mm. So this is given as 1.6 mm. What is the approximate value of P? So as we discussed just now, that the for a approximate to the first order, this the distance of this tapering or uh, this chamfering, so that this chamfer length should be equals to P should be equals to 1.8 times W, and W is given as 1 point. So this is 1.8 times. So it is given as so just yeah. Uh, this is given as 1.8 times, and then so basically like for from the epsilon r is given, which is 2.2, height is given 1.6, and z naught is 50 ohm. Then basically you can with these parameters you can calculate what is the width of the line actually, because height is given. So no, this is not this. So basically we need to calculate this width. This is the width. So if you calculate the width, this width of the line, you will find that the width is equals to around uh, 4.93 mm. And if you calculate this P just by multiplying by 1.8 times 4.93, which will be equals to approximately 8.9. So this formula to calculate the width is given the equation for the microstrip line. So if you have any doubt in this, so you just ask. Otherwise, we will move to next problem. Okay, so let's just move to next problem. Uh, in a Miltrate bend microstrip line as shown is additional metal that is removed in the vicinity of the kernel act as a further act as a shunt capacitance actually, because like all the this will prevent the impedance mismatch. So basically because of the banding some impedance mismatching is there. So if you add a equivalent shunt capacitance to counter that additional impedance mismatch, then basically you can achieve the matching. So basically this behave as a the effect of adding this is basically to add a shunt capacitance to have the impedance matching in those. So the correct answer will be the second one, which is shunt capacitance. So let's move to this line. So a microstrip lines is shown in the figure below, where W1 and W2 are represent the width of the line. The step discontinuity can be modeled as a first order as a shunt capacitance. Actually, basically this will behave as a capacitance. So basically, this is so to know why it will behave as a capacitance, basically you need to solve this discontinuous boundary condition at these two transmission line, and basically this will behave as a shunt capacitance. So let's just move to next problem. What is the value of R2 if R1 is 10 ohm and S11 is 0? So this S11 is 0, S11 is equals to 0 means reflected power at 1 equals to 0 means the Z input impedance is matched. So that means Z input impedance is 50 ohm if this line is 50 ohm, and let's say if this line is terminated by given that the line is terminated by 50 ohm. So this resistance is 50 ohm. So let's calculate what is the input impedance. Uh, so the what is the value of R2 if S11 is 0? So now S11 is basically if you terminate this line with the 50 ohm impedance, and if you don't have any reflections, and this is 10 ohm, this is 10 ohm. So you can calculate the input impedance is basically 10 plus uh, 10 plus uh, uh, 10 plus this will become 60. So 60 times R2 divided by 60 plus R2. It will be equals to the input impedance, which is equals to 50 ohm. So this will become 60 times R2 divided by 60 plus R2, which will be equals to 40. And you can write as this 4 will go, and this will become 1.5, and this uh, 60 plus R2 will be equals to 1.5 times R2, and R2 will be this will become zero point 0.5 times R2 will be equals to 60, and R2 will be equals to 120 ohm. So the correct answer will be 120 ohm. So this was just very straightforward question. Yeah. So the the power splitter shown in the figure is matched with the terminated match when terminated output with Z naught has a large bandwidth. Actually, if you terminate this power, if there is no reflection, then basically it's the perfect powered splitter. And if there is some reflections, actually, then basically it just couples some power to this other port. But if you terminate this with a uh, large large impedance, so the reflection then basically it will have like the wider bandwidth, because this all the characteristic impedance, if you terminate this with the matched impedance, the input impedance is Z naught actually with this network. So basically you can achieve like the matching at all the frequency, and this Z naught is this independent of the frequency. So your bandwidth is approximately large or infinite. So the correct option is Z naught, and which is and the bandwidth is large. So if there in any doubt in this, so you can ask, or otherwise we'll move further with the next question. I will pause for some time. If you have some doubt, then you ask. Okay, so let's just move to next problem. Let's just move to next problem. When the power is incident at the port 3 and 4, so the power is incident at the port 3, and power is incident in the port 3 and port 4 of the magic T. Which of the following two will have output? So so this so the this if you add this b3 and equals to b4 equals to 0, and basically b1 is equals to your 1 by root 2 times a3 plus 1 by root 2 times a4. Similarly, b2 is 1 by root 2 times a3 minus 1 by root 2 times a4. So basically, like if you fed the power to this, then you will have basically like the power will be flowing on second and three, and like the other ports are matched, so there won't be any reflected power. So the correct answer will be 1 and 2. And because like there is no question is given like how much power is there, so we will take a journey power. So with this, let's just move to next problem. So next problem talks about for achieving coupling factor of zero point 0.3, even an odd mode impedance of a coupled lines are. So basically, the Z naught of even mode impedance is given as 1 plus C by 1 minus C, and Z naught of odd mode impedance is given as Z naught square root of 1 minus C divided by 1 plus C, where C is the coupling factor. So square root of 1 plus C by 1 minus C, you can calculate square root of 1 plus zero point 0.3 divided by 1 minus zero point 0.3 equals to the 1.3 divided by zero point 0.7, which will be equals to, if you take square root, which will be 1.3627. And then basically like so Z naught uh, so and similarly 1 minus C by 1 plus C will be square root will be equals to 1 by 1.3627. So that you can calculate. Z naught even mode impedance you can calculate 50, which is the characteristic impedance type 1.3627, which is equals to 68.14 ohm, and Z naught odd mode impedance will be equals to 50 by divided by 1.3627, which will be equals to 36.6 or 7 ohm. So the correct answer will be even and odd mode impedance are 68 and 36. So this first option is wrong. Second option is wrong. Fourth option is wrong. Third option is correct. So this was just like for example like this was the just bare a simple formula substitution kind of problem. So let's just move to next problem. So with this, let's just move to next problem. So so basically rat race junction. So basically a rat race is defined as like because like the rat race junction means like the reflection, all the reflected port powers are basically like 180-degree phase shift apart. So basically like let's say some junction is there, so three port junction is there. If let's say you are feeding power 1, 2 and 3, so the 2 to 3 actually the are phase shifted by 180-degree. So if you try to fed the power to this, only like one of the impedance match you can get. So basically like this is known as the 180-degree hybrid actually. So where the your phase shift between your output port is 180-degree. So then basically so this was the rat race circuit, and which is and that is basically is the example of hybrid coupler. So this is a particular example of hybrid coupler. So then basically if a so if we move to next problem, so if a coupler is lossless and reciprocal, then what is the maximum number of ports it can be matched? So basically a lossless and reciprocal is there. So if lossless and reciprocal network can be matched to all the port actually. So for example those all those passive device and those kind of devices only the condition of uh, reciprocity does not hold. So basically, if we can see this table, so in the case of non-reciprocal devices, all three are not possible actually. So either you can achieve lossless and reciprocal, then matching is not there, and if your is this lossless and reciprocal, uh, if lossless and if this is the if this is like both lossless and reciprocal, so basically then you can four port device you can match all the impedance actually. So the then what is the maximum number of modes it can be matched is all the three modes actually. So if a three-port network is if a three-port network is lossless and reciprocal, then maximum number of if the three-port node is maximum lossless and reciprocal, then maximum number of ports can be matched to one only. Otherwise it will be there will be for example circulator, so only 1 to 2 its matching is there, 1 to 3 is not allowed, and 2 to 3 matching is there, so only 1 to 3 1 to 3 is isolated basically, so matching can't be achieved in the that port. So basically in the three port network only one port can be matched at a time actually. So that is and also you can see from from the S matrix of lossless and reciprocal network. So that with that actually you can match only only one port with the three port network actually. So for four port network, actually you can match all the port even if you have for a lossless and reciprocal network. Actually, that's why your couplers are important in that sense actually. So this was the few problems at my end. So if you have any doubt related to the content which I presented in today's class, so you can ask, or otherwise we will end this session for today, or we will meet next time in the same session. So all the problems actually you tried this solving these three problems for this week, and just let me know the doubt which you may have for this session this week. So I'll just wait for if you have any doubt for this session, or any doubt related to the previous session, or any session which was covered in the lectures, or any other doubt which was which is related to the content which was covered in this week, or content I have presented, or the content which you may have any doubt related to any problems for this week content. So let me just, so this was the summary for this week. So this other kinds of hybrid couplers are also there. So basically, like you can have uh, other kind of coupled line couplers, also example of like that, the coupler you can go. So basically, like others, like those kind of also, like the hybrid couplers are there. So basically, like those, you can analyze by this even and odd mode impedance analysis, and basically you can have like the this equivalent odd and even uh, mode uh, mode capacitance and like impedance actually. So basically, like that, so you can design those coupled line couplers. So so basically, like let's say this, you can model like this. So these are two transmission line, and those are gap coupled by this line. So this is 3 port, this is 1 port, this is 2 port, this is 4 port, and like there are two kind of impedance will exist, even impedance and odd mode impedance, and basically this is z naught. And so you can write uh, so that basically you can convert it to this equivalent network. And if you draw the cross section of this line, so basically like you can write as two lines which have the width of w, and basically the spacing is s. So this you can model with this uh, with the capacitances. So basically, like the you have this ground and like the coupling capacitance. So you can model this by C11, and also with the C12 and C22. So this is C11, this C12, and this is C22. And that odd mode impedance is basically the effective capacitance you can write as a C11, and then basically if you terminate other lines as with the match load, so your effective line capacitance will become a C11, and then your both your Z even mode impedance will become L by C effective, and this you can write as 1 by phase velocity times C effective, and that basically you can write as a 1 by Vp by C11. So others you can write in the case of uh, in case of like that, other symmetry argument you can write uh, as like other port you can write as a C effective will be equals to C11 plus 2 times C12. If you take symmetry, then ZOO will be equals to 1 by Vp divided by C11 plus 2 times C12, and that will be less than equals to ZOE. Even mode impedance is larger compared to that. So basically, in that, basically you can analyze uh, those coupled line hybrid coupler also. So that was the particular derivation for the for the coupled line hybrid systems, and that you can use for having this uh, so that basically you can analyze by this even and odd mode impedance for example. So so basically, so this was the content which I presented for this week. If you have a doubt related to the content which I presented, or whatever the covered in the class, so you can ask in the next class. So if there is no doubt further, then we can end this session for today. We will meet next week in the same time, in the same slot. So till the time you keep enjoying learning this NPTEL lectures, and have a great time ahead. Thank you so much. Have a great week and good night. So I think this is done for the day. So let's just end this session. We will meet next time in the same session. Thank you so much. Bye. Have a nice time.